So we will be starting with a new module today, which is called as network functions. So what are network functions is, they essentially give the relation between currents or voltages at different parts of a network. So for example, if I have a two-port network, oops, so this is what a two-port network, because it has two terminals on the two sides. So this is V1, this is V2. So this is called as port 1, this is called as port 2. This is what a two-port network. And the current flowing is, let's say, I1 and I2. So this is any arbitrary network here. So you can say here I have a series resistor, one single resistor, or a series resistor, then inductor, then capacitor in parallel, and so on. So any our usual RLC will be here, and then we'll give the input from here, and let's say we'll take the output from here. So this will be called as what? Input port, and this will be output port. So usually what we require is, we require relation between various things here. For example, we may require V2 by V1. Then someone might require, for some application, we require V2 by I1. So you might be studying EDC, right? So there you might have studied about voltage gain. So V2 by V1 is nothing but voltage gain. Similarly, you might require current gain. So I2 by I1. So this stuff we require. So this is where as network functions essentially come into picture. So that is why we study these topics. Okay. So let's see what are the terms associated with this. So this is what a two-port network. But if I have only one port like this, so this is 1 prime. So this will be V1 only, and I'll have a current I1 only. So I'll find quantities like only V1 by I1 and I1 by V1, etc. Right? So this is what a one-port network. So what we say here, so the network function is called as here driving point function. Okay. So what is driving point function? So if the excitation and response are measured at the same ports, then the network function is known as driving point function. So if you are talking about one port, only one voltage and current are specified, and hence only one network function can be defined. So for driving point functions, so first which we have is driving point impedance function. So as it says, it is an impedance function, right? And since we have only one port, so we will not write Z1, since it is one port only. So impedance is what? V by I. So Z of S is V of S by I of S. So we already go in Laplace domain, because as we saw, it is simple. Then since we have impedance function, obviously next what will we have? Driving point admittance function. So it will be denoted by what? Y of S, and it will be reciprocal of Z of S. Right? So this is what happens for what? One port network. But if I have a two port network, what will happen? I'll have a driving point impedance function again. But what it will be given as, now since there are two ports, so I'll have to mention the port numbers. So this is for what? One port network. So here I am writing for two port network. Okay. So if I am writing driving point impedance function for two port network, so I am talking about driving point. So I'll take only one port, excitation as well as response. So Z11 is what? Then V1 of S by I1 of S. Similarly, what will be Y11 of S? It will be I1 of S by V1 of S. Similarly, you can do this as port 2. So Z22 of S will be V2 of S by I2 of S. Right? So similarly, you can do Y22 of S. Right? So these are what? Driving point functions. Means you can say that excitation and response is measured at the same port. Okay. So then we have transfer functions. So transfer functions are essentially the ratio of Laplace transform of output to the Laplace transform of input. So in other words, the ratio of response transform to the excitation transform. Okay. So here we have first thing as voltage transfer function. So it is, what is it? Voltage transfer function. It is defined as the ratio of voltage transform at one port to the voltage transform at other port. So what was driving point function? They were talking about one port only. So if you are, even if you had a two port network, you are either talking about port 1 or port 2. But since this talks about transfer, so both the ports are considered here. So voltage transfer function standard is G12 of S. So it is what? Again, output by input. So port 2 by port 1. But if you are saying G21 of S, then it is 1 to 2. So it is always goes from right to left, remember. So this will be V1 of S by V2 of S. So then we have similarly current transfer function. So it is denoted by alpha of S. So what will you have? Alpha 1 2 of S. So again 2 to 1. So it is current. So I2 of S by I1 of S. Similarly, you will have what? Alpha 2 1 of S. Right? So what it will be? I1 of S by I2 of S. Right? Then you have two more, which is transfer impedance function. So what it can be? 1 to 2 Z12 of S. So it will be what? Voltage by current is impedance. So V2 of S by I1 of S. Right? So 2 to 1. Similarly, you can have Z21 of S. What it will be? V1 of S by I2 of S. So then finally you have transfer admittance function. So since it is admittance, sorry, so it will be Y12 of S. So I2 of S by V1 of S. Similarly, you can write Y21 of S equal to, right? So again 2 to 1. So here 1 to 2. So 1 to 2. So you can see 1 to 2. So 1 upon 2. Right? So let's jump to simple numericals based on this. You get a very simple 5 marks numerical for this. Okay. So let's say it is determine the driving point impedance function for the following network. Okay. So this is R, then L, and then we have C. So this is which type of network? One port network, right? So this is R, L, C. Okay. So what we do? So as we saw, we are always in the transform domain, right? So what we do? We write the transform network is shown below. So what happens in Laplace domain for R? It remains as R only. What happens for L? It becomes Ls. What happens for C? It becomes 1 by CL. And what they have asked? Driving point impedance function, means they have asked Z of S. So we are trying to find Z of S as seen from here. Right? So it will be what? So all these three are impedances, so it will be just be a series parallel combination. So these these two are in series, and that combination is in parallel here. So what will be Z of S? So therefore Z of S equal to, so series is R plus Ls. Right? So this is in parallel with this. So R1 R2 upon R1 plus R2. So let's say this is R1. So into R2 is 1 by CS upon addition of these 3 plus Ls plus 1 by CS. Right? So then what you have to do? Multiply by CS. So R plus Ls upon RCS plus what it will be? R, you are multiplying by CS. Right? So L C S square plus 1. Right? So therefore Z of S will be what? So we again always try to keep coefficient of S square as 1. So it will be R plus, and this S was also 1. So S plus R by L upon, so we are taking what common? L common here, right? So it will be L times S plus R by L upon LC times S square plus, this will become what? R by L. So R by L S plus 1 by LC. So LL will get cancelled. So this is your final answer. Simple. So let's go to the next one. Again, same question. Determine driving point impedance of the network. So now they have already given it as transform. So you don't have to worry about taking the Laplace transform or going into the S domain. So driving point impedance is again what? Z of S. So 2S, 2S, 1 by 2S and 1 by 2S. So again these two are in series, right? Sorry. Then this series combination is in parallel with this, which is in series with this. So you can use one step only in the exam also. So this is in series with this, and this two are in parallel. So 2S plus R1 R2 again. So 1 by 2S into 2S plus 1 upon 2S upon addition of this. So 1 by 2S plus 2S plus 1 upon 2S, right? So equal to 2S plus, what you can do is, so 1 by 2S upon 2S plus 1 by 2S upon, so make this 2S common. So what it will be? So this will be 4S plus 2, 4S square plus 2 in fact. So 4S square plus 2 upon 2S. So this 2S and this 2S will get cancelled. So it will be 2S plus 2S upon 1 plus 2S upon 4S square plus 2. So then cross multiply. So you can solve this, right? So you will finally get Z of S, right? So this is simple mathematics, so I am not doing it. So the thing is, I can solve more sums. So let's go to the next sum. It says, yeah. So now they are asking, find the driving point admittance of the network shown. So remember, they have not asked impedance now, they have asked admittance. So be careful while reading the questions. So what is happening here? These two are in series. In fact, these three are in series, but this is a parallel combination. So first we can find Z of S, then we can invert it. So 3S plus 1 upon 5S, this is 5, plus series combination, right? So S into 1 by 2S upon S plus 1 by 2S. So what will this be? 3S plus 1 by 5S plus, this will be S upon 2S square plus 1, right? So what is the LCM? 10S square, is it 10? Yeah, 5S into 2S square plus 1, right? So upon 5S into 2S square plus 1. So what will this be? 30S raised to 4 plus 15S square plus 2S square plus this is 1 plus this is remaining, so 5s square, right? So to get 30s raised to 4 plus 15, no sorry, 17, not even 17, 22. So 30s raised to 4 plus 22s square plus 1 upon 10 s cube plus 5s, right? So what will be y of s? 1 by z of s. So it is just the inverse of this, right? That you can do. So as I said, these are very simple trivial sums. So let's go to the next question. So now it is asking transfer impedance. So find transfer impedance function z12 of s. So this is r, this is 1 by cs. So since it is transfer impedance, obviously it should be what? A two-port network. So how will you solve this? So it is transfer, sorry, impedance, right? So z12 of s. So what is it? v2 of s by I1 of s, right? So basically you have to find this v2 of s, and this is given as I1 of s. Okay. So what will this voltage be? Can you think? Just think over it. So if you have actually thought over it, so this voltage is nothing but the voltage which is dropped here. Right? This voltage is, these two are in parallel. So this voltage is nothing but V2 of S. So what is the current flowing here? I1 of S, because this is open, remember. So current I1 of S is flowing here. So what is V2 of S? I into Z, Ohm's law. So I1 of S into this impedance. So this is parallel combination. So R into 1 by CS upon R plus 1 by CS. So equal to, and I want what? V2 of S by I1 of S. So therefore V2 of S by I1 of S equal to, so R upon RCS plus 1, right? So this is nothing but Z12 of S, but I want coefficient of S to be 1. So remember this in the exam as well. So RR will get cancelled. So 1 upon C times S plus 1 by RC. I can skip the steps, you cannot skip the steps. Okay. So let's do the last sum for today. So it is asking find voltage transfer function. So you can consider this as a voltage gain only, which you are studying in EDC. So this is V2 of S, V1 of S, R 1 by CS. This is I2 of S, this is I1 of S. So what you need to find is voltage transfer function. Means what you have to find? V2 by V1, right? So when you will get V2 by V1, so let's try to find V2. So I can use voltage division rule here. So by voltage division rule, what will be V2 of S? It will be total voltage. What is the total voltage? V1 of S. Sorry, not equal to into. What it will be? This resistor or impedance 1 by CS upon total impedance. So R plus 1 by CS. So simple voltage division rule which you have used in BW. So therefore V2 of S upon V1 of S equal to 1 upon RCS plus 1. So this is 1 upon RC times S plus 1 by RC. Right? So therefore V2 of S equal to upon V1 of S equal to 1 upon RC upon S plus 1 upon RC. Right? So these are final answer. So aren't they very simple sums? Okay. So we'll stop here.